Okay, we're back. This is Stats 189. We're looking at Review 2, and we're on page 3. So state whether the variable is discrete or continuous. Number 13 on page 3. The number of books in the West Campus Library. That would be a discrete, an example of a discrete, not a continuous. Discrete means it can be counted like whole numbers. So if you can count whole numbers, and let's say you have to use whole numbers to count, then it's discrete. So that one is discrete. How many people in a class? That's going to be discrete because you have to count the numbers. It won't be a decimal. It isn't like measured. You didn't measure somebody and go, oh, they weren't tall enough. They only count as 0.98 of a person or something. All right. State whether the variable is discrete or continuous. The time it takes to have a medical exam. Okay, time is always going to be a continuous variable, not a discrete variable. Time is measured, so we can measure it in minutes, we can measure it in seconds, we can measure it in microseconds, we can measure it in hours, we can measure it in months, we can measure it in days. It's continuous because when you measure something, dependent on how precise you measure it, changes what the answers could be. And so usually when you're measuring things, it's considered a continuous variable, and when you're counting things, it's considered a discrete variable. Okay? So like weight, that would be continuous because you're using something to measure the weight. Where, like I said, counting the people in the class or something, that would be discrete. Weight would be continuous. I'm not sure I said that right. Weight, measurement, is continuous. Anytime you're measuring, it's continuous. Anytime you're counting, it's discrete. Okay, number 15. Let X be a random variable denoting how many people get help at the drop-in tutoring center. Each teacher sees 4 to 8 students per hour. The probability that a tutor sees 4 is 0.117, 5 is 0.123, 6 is 0.295, 7 is 0.328. Find the probability the tutor sees 8 in an hour and fill in the probability distribution. So probability distribution looks like this. You have a list of the outcomes going across the top. So since this is people being seen, this would be a discrete, not a continuous. All right. Probabilities were handed to us. We didn't make them into percents. We'll just leave them as decimals here. I think the answer we're going to put in a percent though. And 0.328. And they didn't give us 8, but we can find it, because any discrete probability, this has to add up to 1 total, okay? Or very close to 1. If they give them all to you and it's a little over 1 or a little less than 1, a lot of times that's because of round off error, okay? But if it wasn't rounded at all, and you know, it should add up to 1. Okay, so that's what we're gonna kind of use the reverse of that. If all of these have to add up to 1, but if we have most of them but we're missing 1, the way to find it would be 1 minus adding each one of those probabilities together. So you add those all up, and that works out to be 0.863, and then 1 minus 0.863 is 0.137, and that is not approximately, exactly 13.70%. Okay. So 16, find the probability using the standard normal distribution. Okay. So let's see here. The probability Z-score is between 0 and 0.95. So we look up 0 on our chart, and that gives us 0.5000. We look up 0.95 on our chart, and 0.95 gives us 0.8289. And now let me show you how that chart works. And we're going to subtract those two values. So I will draw a picture here. We'll get rid of the distribution. But first, let's take a look. You have your important formula sheet. If you don't have that, you can print that off from Blackboard. I've got it right next to the tests. And so you want to go to table E, but we want the positive table E. So that's this part. So table E and 0, Z is 0, is 0.5000, okay? If we go to 0.95, what you do is you go down to 0.9, that's right here, 0.9, and now we follow it over. That's 0.90, 0.91, 0.92, see on the top? 0.93, 0.94, and 0.95. So you looked up 0.9 and followed it over to 0.05 on the top and down. And that's how we get 0.95 is 0.8289. Okay? So that's how we use the chart. So now, if I draw a picture of this, they want the area under the normal curve that is captured by these z-scores. Z-scores are another way of saying standard deviations above or below the mean. So if the standard deviation was 0, that's always going to be dead center. At z equals 0, that's always the 50th percentile. And 0.95, that's not quite one standard deviation above the mean. It's just a little shy of 1 standard deviation above the mean. That's 0.95. And it always goes from the point, the z, down to 0. So 50% is giving you this area. And then 0.95 is giving you this area. And what we actually want is this area. So just that little piece that's in between. So you don't subtract 0.95 and 0.5. We look up the values. This is the 83rd percentile. This is the 50th percentile. And so 0.8289 minus 0.5000, that gets us our correct answer, which is when you actually subtract those on number 16, what do I end up with then? 0.3289. Okay. And so these, it doesn't say round to the 100th of a percent, so you just leave it as a decimal for these. Okay. All right, let's do the next one. So that was number 16. Number 17, we're going to find the probability z is greater than 0.82. So again, you use the chart, you look up 0.8 on the left and follow it over until you see 0.02 on the top. So 0.82 is 0.7939. But now we have to be careful because that again, it's not quite one standard deviation above the mean, but it's giving you this area. But look at what we want. We want the area bigger than that. We want to know when z is greater than that. So we want this area. So when we look that up, the z equals 0.82, and we get 0.7939, that denotes this area. except I don't want that area. I want this area. So I have to do 1 minus 0.7939. And so that is how I get that answer of 0.2061. Okay. Number 18. Find the probability, the following using the standard normal distribution. So they want it between -2 and 1.56. Okay. So again, probability that z is between -0.2. It's less than z is less than 1.56. So that's really close to the center. Let's draw a picture. -0.2 is just below the halfway line. Just a smooch below there. Almost 50%, but not quite. And then 1.5 standard deviations above is between 1 and 2 standard deviations above. And so we look up both of those values on our chart, and now we're going to have to use the negative version. Let me show you on camera here of the negative. So it's same, it's still table E, but the negative 0.20 is right there, negative 0.2, and then on the top it's 0, come all the way down, and it's 0.4207. And then when you look up 1.56, you go back to the positive 1.5 on the left and follow it over. It's 1.50, 1.51, 0.52, 1.53, 1.54, 1.55, 1.56 is 0.9406. So 0.9406. And so again, we want this area in between. So this is all the way down to 0. This is all the way down to nothing on this side. And so we actually want this area. So we subtract those two values. So 0.9406 minus 0.4207. And that's a good problem to put into your calculator. So for number 18, we end up with 0.5199. Almost 52%. All right. Okay, so 19, it says if a sample size, if a sample of size 70 is taken from a population with a mean of 28 and a standard deviation of 9, what does the central limit theorem tell us? Well, the central limit theorem tells us two things. It tells us, the first thing the central limit theorem says is basically whatever the mean is of the sample, we can say that's also the mean of the population. So that's not a problem. Standard deviation is a different story. So for number 19, we could say that the mean is whatever mean they say. So mean of 28, the mean stays 28. When we find our z-score, we still use that as a mean. But as far as the standard deviation goes, we don't get to use that big standard deviation. We've got to make that a lot smaller because it comes from a sample of 70. So the standard deviation is now called the standard error. Let's call it SE. And that is going to be the standard deviation divided by the square root of n. In this case, n is 70. And so it will not have a deviation of 9. It'll have a deviation of just about 1 here, 1.076. Think about that. That makes sense logically. If you go fishing in the ocean, think of the varying sizes of fish. You know, there's little micro fish and then there's huge fish. Sharks are fish, so really big fish. Okay? But then if we take and just scoop up a bunch of sea, we net off a little piece of the ocean and just have a sample of fish, the deviation is no longer going to be from this tiny thing to really huge. It's going to be whatever we captured in our, we'll say, 100 square foot net going around and all the way down. Well, that's going to capture a sample of fish, but it's not going to have this as a standard deviation. It's going to have this as a standard deviation, much smaller. Okay? So a lot less variation. Remember, standard deviation is a measure of spread. So whenever you have a sample, you've got to fix the standard deviation. The mean will still stay roughly the same, but and we get to just reuse the mean. But the standard deviation we have to fix by taking it and dividing it by the square root of whatever the sample size is. All right, so let's look at 20. Approximately what percentage of a normal distribution data fall within one standard deviation above and below the curve? Well, remember, on a standard normal curve, we got dead center, and then if we go one above and below, that captures the middle 68%. Two above and below captures 95%, and three standard deviations above and below captures 99.7%. Okay? So it's 68, 95, 99.7. They only want one standard deviation above and below, so that one is 68%. A. 21. When a distribution is positively skewed, the relationship of the mean, median, and mode looks like what? Well, first of all, in a perfectly normal one, mean, median, and mode are all right on top of each other. The mode is basically the highest point. The mean is right in the middle, also right on top of the highest point. And the median splits it into two equal areas, so that's right there. So mean, median, and mode are all in the same spot when it's all centralized. If it's positively skewed, that means you have a big lump here on the low end, and then it gets shot off to the high end. So think of a big stack of blocks, and if you knock the blocks and they go flying this way, that's where the skew goes. So positive skew looks like this, negative skew is flipped around the other way. So the mode is still right here. Okay, now we need the median and the mean. The mean will get pulled towards the whale's tail. So like if you think of this as a whale above, in the ocean, there's its fin, there's its head. The mean gets pulled down a lot. And then the median is just the middle point. And so that'll be a lot closer to the mode. The median is what we call a resistant measure. So this choice is B, mode, median, and mean when you have a skewed positive. All right? So if it was skewed negative, that would all just reverse. Then you'd have a mean, median, and mode. All right. Let's look at 22. So we've got, suppose that the top speed of a population of cheetahs is normally distributed, we're on page 4 now, normally distributed with a mean of 70 miles per hour and a standard deviation of 8 miles per hour. Okay, so they're going to have us apply the central limit theorem on this one. So for part A, it's just based on the population. So find the Z-score of a cheetah whose top speed is 62 miles per hour. Well, that's slow. 62 minus the mean, 70, divided by the standard deviation, 8. It's negative 8 over 8. That is negative 1. There's one standard deviation below the mean. So amongst the population of cheetahs, it's pretty slow. It's one standard deviation below the mean. But if we look at a sample of 40 cheetahs, the 64 minus 70 stays the same, but that standard deviation is now going to be 8 divided by the square root of 40. So that is going to be a lot different of a standard error instead of a standard deviation. So we still have negative 8 on the top, but on the bottom, I could do that on my calculator here. 8 divided by the square root of 40 8 divided by the square root of 40 is 1.2649. I'll go about 4 places out. There's still more after that, but I'm just going to leave it 4 places. And so negative 8 divided by 1.2649 is negative 6. Wait, that's not what I have here. Oh, wait. It wasn't 62. It was 64. They changed this. Sorry. They changed the speed. That was 62. I wrote 64, but 64 minus 70 is negative 6. So they changed the speed. So negative 6 divided by 1.2649 is negative 4.743. We'll just call it negative 4.74. So now look, out of 40 cheetahs, it's super duper slow. It's almost 5 standard deviations below the mean. In the whole population, there's some slow ones, and it's not the slowest of the slow. But in a sample of 40, it's very slow. Even though it's a little different. This is 64 and that's 62. So they kind of changed the speeds up there. All right? But that was still applying the central limit theorem for the second part. First part was just a standard z-score. All right, let's look at 23. Suppose that the age of a car in the United States is normally distributed with a mean of 8.3 years and a standard deviation of 0.7 years. Draw and label a normal distribution curve representing the distribution. Do not use the standard normal with z-scores. So they don't want 0 and 1 and 2 and 3. They want the actual values. And we'll label them 1, 2, 3. So this is an unstandardized curve we're doing here. 23. So this is 0. This is 1. This is 2. This is 3 standard deviations above the mean. Negative 1, negative 2, and negative 3 below the mean. But now you do the 8.3 is the mean. That's the actual value. Now we add 0.7 to that. So 9-year-old car is 1 standard deviation above the mean. Add 0.7 to that. 9.7 is the car, 2 standard deviations above the mean. 10.4 is 3 standard deviations above the mean. So 1, 2, and 3. And then we go the other way. We subtract 0.7 from each one. So that's 7.6, 6.9, and negative 3 is 6.2. So that's where this would fall. This would be 6.2 years, this would be 6.9 years, this would be 7.6 years, this would be 8.3 years. 9 years, 9.7, 10.4. Okay? So let's look at 24. They want to know what is the probability a randomly selected car is older than 7 years. So they want us to find the probability x is greater than 7. Well, we have to convert that x into a z-score. Okay, so let's do that. So z is equal to 7 minus 8.3, the mean, divided by 0.7, the standard deviation. So the value minus the mean, hit enter, and then divide it by 0.7. So that ends up negative 1.3 divided by 0.7. And so we end up with a z-score of negative 1.857. We'll call it negative 1.86. So now let's draw a picture. Always draw a picture. It's below the mean. Think about where 7 is. 7 is hitting just about right here. So it's from there up, though. So we want from here up. All of that. And so when we look up negative 1.6 on our chart, we get 0.03 0.03, where's my word? 0.0314. Okay, but that is this part. That's 3%. We want this part. So we're going to do 1 minus 0.03. That's why it's good to have a picture, because when you look at this, this doesn't look like 3%. This looks like 97%. And so we subtract that and get 0.9686. And then we make that into a percent to thousands, or to hundredths. So 96.86%. Almost 97% of the cars on the road would be greater than 7 years. And only 3% would be less. All right? According to this theory. Okay, next video will be on page 5, 6.